Continuity. So what is continuity? A function f is continuous at c when f of c is defined, limit of f of x as x approaches c exists, and the limit and the value at c are equal. And here's some examples. So here in this first example, let's see at this point here, let's call it c. F of c is not defined. And because f of c is not defined, it means this function is not continuous. Here's another one. You see that? Let's call this point c. The limit as x approaches c of f of x does not exist, since it approaches two different points at c. And since the limit does not exist, this function is also not continuous. And just last one here, the limit as f approaches x, notice that the limit as f approaches as x approaches c, the limit as x approaches c is this value right here. It exists, but it's not equal to the actual value at c. And since the limit and the value are not equal, then the function is not continuous. Now let's say we have a function like this. This is c. You can say that f of c, it's right here. It's like some value. The limit as x approaches c is that same value right here. And the limit and the actual value as c are the same. Now, a much simpler way to explain continuity is if I was drawing a function, if my pencil does not leave the paper, then the function is continuous. You can see it's just like one solid line. If the line was like this, it would also be continuous. It's still just one line. I'm not picking up the pencil to do anything. If I had to pick up the pencil, let's say do that, now this function here, this is not continuous. You're going to have three main types of discontinuities. These discontinuities are points where the function is not continuous. This first discontinuity right here, it's called a removable discontinuity. You can see this point right here is sort of removed from the function. So we identify a removable discontinuity. Another one, this is called a jump discontinuity. As you can see, the function sort of jumps from this one point to the other point, which makes it not continuous. This final one here is called an infinite discontinuity. Basically, that's your vertical asymptotes. Your vertical asymptotes are places where you'll have infinite discontinuities. They're not continuous. Right here. Let's work through some examples. Hey, this function here, f of x, and you want to evaluate the limit as x approaches -2 from the left. So you can do that. This arrow, you follow the function from the left, and it's approaching 2. Now say the same thing, but from the right. You can see it approaching from the right. Now that's -1. Since these two aren't equal, that means the limit as x approaches -2 does not exist. Let's also evaluate here f of -2. Because the function's shaded in right here. So it's actually defined at negative 2. The value itself is 2. So is f continuous at x equals negative 2? And there's no, because the limit as x approaches negative 2 does not exist. Since the limit does not exist here, you can't call this function continuous. This function sort of jumps from 2 to negative 1 right here. You have a jump discontinuity. Let's do another one. It's the same graph here. Now we're going to evaluate it at 3. So the limit as x approaches 3 from the left, you can see it approaches 0. From the right, it also approaches 0. So that means since these values are equal, you can write that the limit as x approaches 3 of f of x is 0. But notice here that the actual value of 3 is at negative 1. The graph is shaded in right here. And so that means f is not continuous at x equals 3, because the limit as x approaches 3 of f of x, which is 0, is not equal to the actual value at 3, which is negative 1. When you have a situation like this point is removed from the function. You have a removable discontinuity. Alright, so find all points of discontinuity for f of x equals x plus 5 over x squared plus 2x minus 15, and describe each type. If you get a problem like this, the first thing you're going to want to do is you want to factor it out. If you're going to factor out this quadratic, the two numbers that multiply to get negative 15 and add up to 2, and 5 and negative 3, we have x plus 5, x minus 3. And you leave it like this, because now, if you notice, you have this looks familiar, you're going to have a hole right here at negative 5. You're going to set x plus 5 equals to 0, so x equals negative 5. So when you have a situation like this, if you plug in negative 5 into the equation, you're going to get 0 over 0. That means you have a hole. What the hole means is it means you have a removable discontinuity in this function at x equals negative 5. And this other part, x minus 3, into the denominator, and if your x minus 3 is 0, it means x equals 3. If this x minus 3 is equal to 0, then the function would be dividing by 0. And so in that case, it would be an infinite discontinuity at x equals 3. Give me a chance to graph this real quick. So if I did the function looks something like this. We're at x equals negative 5. You're going to have a hole here. The function is actually not defined at this point. It's a hole. It's a removable discontinuity. And at x equals 3, you have a vertical asymptote. And that vertical asymptote is basically the same thing as an infinite discontinuity. So the function is not continuous at these 2 points, x equals negative 5 and x equals 3. And they may be given a piecewise function and be asked to prove that f of x is continuous. So since your break in the function here, your break in the piecewise function is at 0, you're going to plug in 0 for these. So the first step is to set the two parts of the piecewise function equal to each other, because the result of this is going to be some y value, and the result of this is going to be some other y value, and these two y values have to be the same for it to be continuous, and that's why we're writing an equation here. That's why we're equating these, because these have to be the same in order for f of x to be continuous. And here, since the break in the piecewise function is 0, you can plug in 0 for x. And start simplifying. So the cosine of 0, remember from the unit circle, the cosine of 0 is 1 e to the negative 0, so that's just e to the 0. And anything to the 0 power is just 1. So e to the 0 is 1 minus 4. So negative 3 plus 1 is negative 2. 2 times 1 is 2. 2 minus 4 is also negative 2. So now you've proven that, well, here we didn't write it out, but this negative 3 plus cosine x is the limit as x approaches 0 from the left. And this 2e to the negative x minus 4 is the limit as x approaches 0 from the right. So if you're asked to prove that f of x is continuous, first step is to want to define, or to find the value at this break here. So f of 0, we just found that, and that's going to be right here. F of 0 is negative 3 plus cosine 0, which is negative 2. And find the limit as x approaches 0 of f of x. We just found that here. That's also negative 2. You're going to have to write down that the limit and the actual value are equal. So you have to write these three things down to prove that a function is continuous. You may also get a problem like this, where you have to find the value of k that makes f continuous at all x. So the same thing as the last one. I'm going to set these two expressions equal to each other. And see that the break in the piecewise function is at 5. So you plug in 5 for x. That's 25 minus k equals 20 plus 2k. Now all you have to do is solve for k. So you add k both sides. 25 equals 20 plus 3k. And you subtract 20. Yeah, 3k equals 5. So k is equal to 5/3. So plugging 5/3 for k into this piecewise function will make the function f continuous.